Hey there, Calc folks, back here with another video lecture in my series of lectures looking at multivariable functions. In my last video, I introduced you to the case for a multivariable function, right? And we looked at their domain and range, right? How do we explore their inputs and their outputs? We looked at making them into tables, right? Just, looking at evaluation and solving these function types. And then we could even consider, we looked at being able to, imagine these things graphically. What would these look like as surfaces in three-dimensional space? And gave you some technique for going about and developing those surfaces. And that's what we looked at up to this point, right? Just an introduction to what it means to be a multivariable function. All right, and some of the intricacies in regards to them, right, and what it means to be functional in multiple variables. All right, we're going to continue then now with that study of multivariable functions, where we're going to now kind of delve into the realm of calculus, where a lot like what we saw going on with single variable functions back at the beginning of our studies, way back in Calc 1. With single variable functions, one of the first calc operators that we considered applying to that function was the case for a limit. All right, we looked at applying limits to f of x back in Calc 1 in this two-dimensional context, right, in this single variable context. Well, we can perform that limit operation, right? We can perform that limit operation on multivariable functions as well, right? And see a similar understanding. All right. This is what you will see in my notes. If we bring over my notes here on this material, right, I am going to delve into looking at limits of multivariable functions. I am going to, talk a little bit about their meaning to begin with. We're not going to spend a lot of time with the definition of limits. You certainly can look at that definition in the book. It is an epsilon delta definition, where, as we've learned back in Calc 1, that epsilon delta definition there is formality, right? It is formal, whereas we can have a very loose understanding of what's occurring here, right, to understand what it means to be a limit. Right, limits just describe behavior of our dependent value as our independent value does something in its behavior, right, as it approaches a particular input, right, or independent value, right. How does our output behave? That's all limits are really examining. Right, so I'm going to just spend, and that's where I open with my notes is into that, and this is going to bring about then. Taking this understanding multidimensional, what that entails. What that then brings about is what we call the two-path test for non-existence. We're going to take note of that here, folks. And then we're going to look at how do we actually evaluate these things, right? Keeping in mind what comes up in terms of some of the detail involved. All right. How do we then go about evaluating a multivariable function? Some are rather elementary, right? Some of it is more than just a substitution game, whereas others it can become a really complex evaluation process. So we're going to get into that in this set of notes and kind of break it all down for you folks here in terms of evaluating these, in terms of being able to calculate these folks, right? This is what we're going to see. But where I do begin here, right, if you note, is I go back to what I've opened with here already. As with single variable functions, y equals f of x in two-dimensional space, you can take that limit operator and apply it to a multivariable function in 3 dimensions. All right. When applied to a multivariable function in 3 dimensions, this is our understanding. All right. What we have here is a limit where in a multivariable function, our multivariable function being f of x comma y, right? F of x comma y has 2 independent values, x and y. Your domain of this function doesn't consist of one variable value in one-dimensional space. it consists of two variable values in two-dimensional space, in what we would think of as being the xy plane of 3 dimensions. All right? Where here we're going to explore the behavior of that independent variable value here, that independent coordinate in our domain, given by the values x and y, and look at the behavior of z, the output of our function, as that independent value given by x comma y approaches this value a comma b. Right? Our output, which we understand is just a single value that exists in one-dimensional space, right, is going to behave a certain way as the independent values x comma y, right, approach a particular value of a comma b in 2 dimensions. Right? And if that limit equals L, we say, right, the way we understand this statement, the limit as x comma y approaches a comma b for function f of x comma y being equal to L, right? The way we understand that is as follows. It means z of f of x comma y becomes sufficiently close to L as x comma y becomes arbitrarily close to a comma b in value. Right? No matter how close we want to be to a comma b in value for the values of x comma y, right, the output of our function z will be close enough to L for us to say, yes, it is L in value. Right? Z approaches L as x comma y approaches a comma b in our 2-dimensional space. Z approaches L in 1 dimension, right, along the z-axis, as x comma y approaches a comma b in 2 dimensions, right, in our xy plane. That is what this statement is interpreted as. We're describing the behavior for that single value variable of the output, which is, if we think 3-dimensional space is tracked vertically in the up or down orientation, as x comma y, right, this location in 2-dimensional space, what we would think of as being the xy plane of 2 dimensions, approaches a comma b in value. Right? How does z behave? Does it head off to infinity? Does it not exist? Or does it approach a real number we could call the value of L? Right? There's a lot of different types of behavior we could consider here. And it's all wrapped up in the evaluation of a limit. The limit of a multivariable function. Now, there is a bit of a difference here. We take note. Now, as you can read, this next statement is how it differs from calculating the limit of a single variable function, folks, right? In the case of a single variable function, we had just x approaching a. And there were only 2 ways that x could approach a back in that instance, right, of a limit applied to a single variable function y equals f of x. X could approach a from values smaller than a, or what we would say is the left of a along our x-axis, or x could approach a from values bigger than a, right, from values to the right of a along the x-axis. And to highlight those differences, we often would have saw a what would look like a power, but with a sign there, a negative for approaching a from the left, or a positive for an approach of a from the right, in this value as x approaches a. All right. However, in the case of a multivariable function and the limit applied to it, in the case that we're considering here, right, there actually exists an infinite number of ways for our independent values x and y to approach the specific value a comma b in our coordinate space. Furthermore, right, in order for L to exist, right, in the statement that the limit as x comma y approaches a comma b for f of x comma y as being equal to the value of L, the value of that limit, on every infinite approach of that coordinate a comma b in our two-dimensional domain, right? In the, what we might say is our domain, which is, let's say, contained in two-dimensional space, right? Z equal to f of x comma y must approach L in value. And I should probably add one other place here. To approach a comma b in the domain of, we would say, function f, which we're going to denote as d. So let's add that little note there, folks, just because we do have to be approaching a comma b within the domain of f, respectively. All right. There's going to be areas where we're going to have limit concerns on boundaries within our domain, right? Boundaries on our domain. So we want to make sure that we are only considering approaches, though, that are happening within that domain. Certainly anywhere the domain doesn't exist, we can't approach that coordinate in those regions. So I do add that in here, respectively. Now, what this leads us to is what we call the two-path test for non-existence of a limit. All right. Furthermore, if any two paths approach a different value for L in the application of a limit, the limit does not exist by what we call the two-path test for the non-existence of a limit, or for the existence, I should really say here, for the, I believe it is, non-existence of a limit. All right. Let's read it here. Notice it does just say if the output of a function, z equal to f of x comma y, approaches two different values, as the input of the function, x comma y, approaches a comma b, right, a specific location in the domain of f, right, along two different paths, right, then the limit as x comma y approaches a comma b in that domain of f of our multivariable function f of x comma y does not exist in value. This is known as the two-path test for the non-existence of a limit. If you can show that any two approaches of that coordinate a comma b within the domain of f give you different values as the value of the limit, you can say that that limit does not exist. All right? This is how we prove non-existence, folks. All right? We have to show that there are two paths that give us different values for the limit. All right? Whereas this does also throw some complexity into actually finding the exact value of a limit in multidimensional space, as there are actually an infinite number of paths for our approach. So, before we only had to have two paths in our approach. We approached A along our number line from the left or from the right, and it was easy to show that A equaled, or that the output of our function equaled L as we approached A from the left, or as we approached A, and as we approached A from the right, to be able to say that two-sided limit existed and was equal to L. Now, we're going to be working in a plane where we're going to be able to approach this point, right, from any infinite number of different directions. So to show that that function's output approaches the value of L on every single infinite approach is certainly an impossible task, to say the least. All right? In the case of continuity, in the case that we are continuous at a comma b, we can use the fact that we are continuous at a comma b to be able to state that the limit does exist and is given by f at a comma b, right? Which is what follows from substitution in some of our cases for evaluating these limits, right? But if our function is not continuous at a comma b, right, or cannot be modeled by some other very similar looking function that is, right, then concluding that a limit for a multivariable function equals the value of L is a bit of a tricky task. And this can first of all begin as a coin flip and then work itself into, certainly higher and higher degree of correctness. But certainly there's always going to be a little uncertainty. Unless we were to consider perhaps looking at the behavior of our function graphically. Right? Remember, the one thing about graphs, it was a bit of a fundamental technique back when looking at evaluating the limit of a function in the case of a single variable functions. With the graph always was good support for our answer to a limit. Right? We could certainly look on a graph and see a point being the point in the case of continuity, or seeing that our limit headed off to positive or negative infinity from both approaches, or maybe even the case of does not existing because we had different values for L in our approach from the left or from the right. That was a bit more of a fundamental technique, and we learned how to get around that with some algebraic technique, right? Including that of L'Hopital's rules, some calculus technique, all right? However, L'Hopital's is not going to be able to be applied to a multivariable function within the context of multivariables. It's still applicable in one variable. If you can get your analysis down to a one variable context, you can apply L'Hopital's, right? But not in the two-dimensional, or not in the multivariable context where you have two independent variables. Is that possible? Right? Your substitution may work, but you're going to encounter those indeterminate forms, right? And that's why I say watch out for L'Hopital's. L'Hopital's is not going to be applicable in the multivariable context, right? Where you're going to have to then consider what could be happening, where graphics is certainly going to be some consideration, right? You're going to develop an analysis for the value of the limit by looking at some different approaches and starting to draw some conclusion for what might be the value of the limit. Certainly, maybe refining its precision along the way, right? Getting better answers or getting more evidence that this could be the value of the limit. But I will warn you, folks, right? You have to watch out for inductive reasoning here. Just because you see a couple of cases show you that something is true doesn't mean that it's true always, right? Graphs do help because they do show you every single infinite approach. But you have to know what you're looking for in the graph. And I'm going to tie some of that in here with evaluating limits. Now, I throw this all out here because I do have another note that follows with just evaluating limits. That is what we're going to get into here, folks, is how do we actually evaluate a multivariable function for a limit? And it is, like I said, not much different from what we've done back in Calc 1, except, right, if substitution rule doesn't work out really quite nicely for us and we can't get things to cancel where we end up being able to apply some substitution, if we're not be able to form some similar looking form, right, with our equation through canceling, and we're stuck with kind of an indeterminate form, we may have to do an analysis that involves looking at different approaches. And we're going to see some of that in our work here. All right? Let me dip into the background here and let you copy down this note. But that is what I say here, folks, in a paragraph. Now, I do see one thing I want to add in here. If the evaluation results in an indeterminate form, I want to put in maybe a statement here. Maybe just quickly say attempt to simplify function f, right? And then maybe we'll add into that afterwards, and or examine behavior of z equal to f of x comma y on several specific approaches, right, of several different degrees. And I'll get into that here in just a moment, folks. Right? When you look at your approaches, you can certainly apply the two-path test for non-existence when necessary to conclude non-existence, right? And then if the two-path test cannot be seen to apply, examine the graph of the surface, traces, and level curves around and passing through this point of approach, right, when it is that case. All right. So here, folks, it does start off always with some substitution, and if substitution produces an indeterminate form, well, then you need to kind of get into what that is telling you. Right? You're going to have to attempt to try to simplify f if you can. Remember, sometimes you can find a factor that maybe cancels between a numerator and denominator that might make it into a similar form where substitution does apply, and or then begin examining the behavior of z equal to f of x comma y on several different approaches if you can't get things to simplify. So I'll quickly just put that in there as that note here. All right? I will certainly illustrate all this in the notes below. All right? Let's see here. If we scroll down and consider a limit, right? First of all, we might consider the limit as x comma y approaches negative 2 comma 4 for this multivariable function given by x squared plus y squared over x minus y plus 1 in value. Now, what you will notice is substitution applies rather readily here. If you substitute in negative 2 for x and you substitute in positive 4 for y, you will have negative 2 squared, which is positive 4, plus y squared, which would be 4 squared, or 16, positive 16, being added together in the numerator. 4 plus 16 is 20, over negative 2 minus 4, which would be negative 6, plus 1 in value, which would be negative 5. And substitution would just yield negative 4 in value. All right? And substitution works here because our function is continuous here. All right? The function is continuous at the point of approach in our limit, right, for z equal to f of x comma y. And f is continuous at a comma b. All right? You want to recall that, right? Note, substitution method works since the function is continuous at the point of approach in our limit. And what we do take note on here is what it means to be continuous. For z equal to f of x comma y, f is continuous at a comma b. We might add this as the next line. If the limit in our approach for f of x comma y equals a comma b, right, f at a comma b. Let me break that out this way. Right? This understanding implies continuity of f at a comma b, implies the limit as x comma y approaches a comma b equals f of x comma y. Well, the limit as x comma y approaches a comma b for f of x comma y exists and is at the definable value of f at a comma b. All right, this all gets into the continuity aspect of it. If the limit as x comma y of a comma b for f of x comma y equals f of a comma b, just equals what you would get when you substitute in, that does imply continuity at that point a comma b. And if it's continuous at that a comma b point, it implies the limit does exist. All right? And what it would exist at is this value in negative 4, right? The value of the limit, the value of the function at a comma b. All right? In the case of continuity, that is why substitution works, folks. Right? If you have continuous at your value of the function and you substitute in and you get a real number back, well, that's because your function is continuous at that coordinate. And that really is not really a big limit concern for us, usually. It's the limit concerns that we have at the edges of our domains and our domain concerns. Right? Let's continue here. look at another example. A case where substitution doesn't work so conveniently. All right. We might consider the limit as x comma y approaches 0, 0 for approaches the origin for x squared over x plus y in value. What you'll notice is if you substitute 0 into the numerator, you get 0. And if you substitute 0 into the denominator, you get 0 plus 0, which is 0 also. You obtain that indeterminate form 0 over 0. Now, this does imply we might need to consider rewriting the function to obtain a real number result, or consider finding a way to apply the two-path test for non-existence. Right? Now, if I attempt to rewrite that, there really is nothing I can factor out of the numerator or denominator that will allow for some canceling and allow substitution to work out nicely for us here, to give us any real insight. Right? What I might consider doing here is looking for a couple of different paths to give me some non-existence. Right? In fact, if you go out and you explore this using some program like Mathematica and consider the limit, right? That's going to give you some insight into what is certainly going to be the value of this limit, but how can we show that insight? All right? I'm not going to say what that quite is yet, but let's look at what some paths tell us first. All right? Where is this note? First of all, what you want to do is take note of your domain. These paths have to exist in your domain. And let's see what our concern is. All right? What is our concern? Can you see the concern in this graph, folks? Actually, let me scroll back up to highlight the function. Here's our function. Let's actually maybe bring that down here. Note the domain of f of x comma y equal to our function, right, is described by this down here. Right? That might be something we want to put in our statement there. Right? Let's highlight this is the function whose domain we are considering. Right? And can you see the domain concern in that statement there, folks? It's down here in the denominator. X plus y is not allowed to equal 0. Well, where does x plus y not equal 0? Well, that's where y does not equal negative x in value. Right? Solving where x plus y equals 0 will get you where y equals negative x. So where x plus y does not equal 0 will be where y does not equal negative x in value. You can also set up that inequality. X plus y does not equal 0. And solve that for y, and you will find that y does not equal the opposite of x. All right? Which is illustrated down here in this following illustration, folks. Our domain is every coordinate in this xy plane except where y is not allowed to equal negative x, right? Where y is equal to negative x falls along this dotted line, right? This diagonal line running through quadrants 2 and 4 in our coordinate space, right? What we might say is the reflection of our line y equals x in this space. Furthermore, if we look at where we're approaching, we are approaching in our limit the coordinate 0, 0. Right? We are approaching the origin in that domain, the exact location where the x and y axes intersect each other, right? The exact center of this graph. This is the point of approach in our limit, folks. And notice where that point exists at. It exists along this line where we're going to have domain concerns. Within our domain, it exists out at a boundary in our domain, folks. And the limit of our function, or the output of this function, could be behaving a couple of different ways. It could be approaching a real number at that bound. It could be approaching positive or negative infinity at that bound, or it could be approaching lots of different values at that bound. All right? And what we have to do is kind of analyze, well, based upon our approach, right? Based upon what approach we approach this point in the domain, based upon maybe approaching this direction, or approaching this direction, or approaching this direction, or maybe even approaching this direction. All right? Where those first three were approaches along a line, where that second one was a bit more of a parabolic approach. There's a lot of different approaches we could consider here. There's an infinite number of ways we could approach that coordinate. All right? We're going to look at the value of the limit for several of those approaches. All right? Start with some linears, some of the simple cases. Where x equals 0, where y equals 0, and where y equals x. Those are our first three fundamental approaches. We could consider approaching the origin where x equals 0. That's along our y-axis. That's along the vertical line x equals 0. We could be approaching along the horizontal line y equals 0. That's along our x-axis. Right? And then we could approach on what would be the reflection of this domain concern, the line y equals x. Right? We could be considered approaching on this line and seeing what is our different behavior, folks. All right, for the output of this limit. And this is what we do down below. All right. I believe I look at the case when x equals 0 and y does not equal 0 first. That is where x equals 0 and y does not equal 0 is along this approach. And y cannot be equal to 0 because we would not be in our domain, right? So we just maybe would make that statement there. But we're going to be approaching 0, certainly, as x is equal to 0 along this line. We're going to still approach 0 in value for y. All right, you can see that on our graph. And that would be given by this limit statement seen here. If you take note here on how I express this limit, right, I took that two-part, well, that coordinate x comma y heading to 0 comma 0 that we saw above, and I broke it down into these two statements. We're going to set x equal to 0 in that statement, and we're only going to consider y approaching 0. Right? To consider the approach given up here in this limit, where x comma y approaches 0 comma 0 in value, I'm going to consider the approach that happens along the vertical y-axis. That's where I'm going to set x equal to 0 and only consider y approaching the value of 0 in this limit. Right? That, like I said, is our approach coming from either above down the y-axis or from below up the y-axis, approaching this origin location in our illustration here of our domain. All right? So I'm going to let x equal to 0 in that approach, and I'm going to consider what would happen as y approaches 0. So if I make x 0 in this limit, that will produce a 0 in the numerator and leave behind just y in the denominator. Where I'll be now interested in what's the behavior as y heads to 0 here. And because the numerator's value is equal to 0, I could go one step further with this. I hope you can see it without this notation, but what we could say here is this is the limit as y heads to 0 for just the constant of 0. And what's the limit of a constant? Well, it is just the constant itself. So the end result is just the value of 0. So right now, what the information is telling us is if I approach the origin in my domain along the y-axis, right, I will approach 0 in value for the output of this function, right? For the output of this function x squared over x plus y in value. As you approach the value 0, 0 in its domain along the y-axis, this function says, hey, I'm approaching 0 comma 0 in my behavior. All right? That's one little bit of information about one of an infinite number of approaches, folks. From that one bit of information, out of what was actually an infinite number of different approaches, you cannot conclude that your limit here is going to be equal to 0. You cannot say that. That is reasoning inductively, and reasoning inductively does not prove anything is true. It only starts to point in that direction. We only have one bit of information that says, yeah, it looks like 0 might be the answer, but we have to explore further. Right? That's inductive reasoning. Right? It points in the direction of what might be true, but it doesn't guarantee that what you are currently observing is necessarily true. Right? It doesn't prove it's true. Right? So let's look at another case. Let's look at approaching along the x-axis. Along the x-axis in our domain, right? Along the x-axis in our domain, we are allowing y to equal 0 along that x-axis, and x is approaching 0 in value. Right? X is not allowed to be 0 in this understanding. Right? We're going to be looking at the limit as x approaches 0 where y is set equal to 0. And if I set up that statement, I will end up setting up x squared over x plus y, right? If I make the y 0, this y in the denominator will turn into 0, and I'll have simply x squared over x in value, which will be the limit as x approaches 0 for x squared over x. Which, with a little simplification, you can cancel an x in the numerator and denominator, leaving you with just one x in the numerator. And we can consider the limit as x heads to 0 for just an x, a linear function, and that is just, through substitution, the result of 0. It also gives us, on this path, a limit result that is 0 in value. All right? It gives us a second piece of information that says, hey, this limit could potentially be 0 in value. But, folks, it's not enough information to conclude that it is indeed 0. All right? 2 of an infinite number of approaches is nowhere near enough information to conclude that it is equal to 0 in value. All right? You might consider a third approach. A third of the fundamental approaches is along the diagonal y equals x here, where if we approach along the diagonal y equals x, the limit as x is going to head to 0 in that case, and we might say y is equal to x in that case. Right? That is along that reflection across the origin or the x or y axis, so I just called it the reflection of this graph, because no matter how we reflect it in a common sense, it reflects into the graph y equals x. Right? But it's this approach here. If we let y equals x and just let x approach 0, how do things behave? That would be on that approach. That would be, or when y equals 0 and, let's say it this way, x approaches 0 in value. Let's consider saying it that way, right? That limit would be stated this way. We're going to let y equals x and let x approach 0. We could also let x equal y and let y approach 0. That would also work equivalently, right? But let's set it up here where we're a little bit more familiar with it in the context of being an x. So if I let y equal x, that would become an x in the denominator, and you'll have an x plus an x, which is 2x in the denominator. And again, you'd be interested in the limit as x heads to 0 for x squared over 2x, which would be the limit as x heads to 0 for x divided by 2. Where through substitution, you again would find that equals 0 in value. These three fundamental lines all seem to show that if we approach along a line, any line, the result might be 0 in value. All right? And I do say that next in the notes here. All right? It does certainly appear most linear paths approaching 0, 0 in the domain of this function produce 0 as a result for the limit. All right? This can be shown for certain Now here is a little deductive reasoning. Now this is just linear paths, folks. But this can be shown for certain, right? Involving all non-vertical lines defined by the equation y equals mx in value, where m describes the slope of the linear approach. This is setting up a very generic, right, line passing through our origin. Notice we are using a little point slope formula here. Every single line passing through our origin with a slope of m, other than the vertical line, which we've already considered is the case where x equals 0, right, can be described by this line seen here, which we build using a little point slope formula. Now, x minus 0 is certainly just x, and mx plus 0 is certainly just m times x. So that's why we do see this simply written as y equals m times x. M being any generic slope that we want to consider. We have already considered the case where the slope has been 0 and where the slope has been 1. That has been our horizontal line and our diagonal line y equals x. Right? Y equals x this way. Right? When I do my illustration here by hand. Right? So, consider what would happen in this case. If I generalize a little bit more and do some deductive reasoning with lines, notice when y equals mx, and let's add in there again, and x approaches 0 in value, right? We end up with the limit seen here, where I can replace this y with m times x, which I see in the next statement here, and just consider the limit now as x heads to 0 for x squared over x plus m times x. I can factor in value of x from both terms here in the denominator. This can actually be written as x times 1 plus m, right? Where I can then cancel a value of x in the numerator with one of those values of x in the denominator. A lot like what happened with the lines described above, right? Which will leave me x over 1 plus m in value, where 1 over 1 plus m in value is actually a constant with respect to the limit in terms of x. Even though it involves the variable m is not considered in the limit, so its behavior is treated a lot like a constant. And the quantity 1 over 1 plus m can be factored out as a constant factor. And what that leaves behind is just x. Right? Factoring x from this quantity will leave x times 1 over 1 plus m, and that 1 over 1 plus m can be factored out of that product. Right? So what is the limit as x heads to 0 for just x? Well, that's 0. So we're left with 1 over 1 plus m times 0, which is anything times 0 is 0 in value. So regardless of what linear equation we put in here that passes through that origin, right, every linear approach is going to give us the result of 0. And you're going to go, folks, all right, that should be enough information, Mr. Sexton, to say that this is the value of that limit. And I'm going to say, no. That does not illustrate every single infinite approach. It does show us an infinite number of approaches. It does show us the result will be 0 for every single infinite linear approach, but it has only considered the linear cases. There are other approaches we could consider that are not linear. We could approach on parabolas and see different behavior. Right? And I believe that is what we see down below here. Right? First of all, I do take note and say, now even with the above results, all indicating the limit may be 0 in value, we cannot conclude this result with 100% certainty. Right? There are an infinite number of approaches we can define passing through the origin in the domain of this function. Not all of them are linear. We might say that here. Not all of these approaches are linear, leaving still an infinite number of approaches unexamined Is that one word or separated there, hyphenated? Let's leave it hyphenated for now. I'll let my spell check it corrected here before I send that to you. All right, before I post it. For example, let me throw this obscure approach at you. Just for the sake of brevity, we're already at 45 minutes. For example, consider the approach defined by the parabolic path y equals x squared minus x. Right? Another way we can think of that approach, that is, if we factored the x times x minus 1 in value in a factored form. And what you can see there, right, is that certainly is an approach that is passing through the origin as a line. Plugging in 0 there for x will make this entire right-hand side 0, so y would be also 0 in value. Or 0 squared minus 0 is certainly a y value of 0. This approach does pass through the origin in the domain of our function. It is obviously not a linear path. It is a parabolic path. It is defined by a quadratic, x squared minus x. All right. We can see its x-intercepts at 0 and at positive 1 in value, this parabola. All right. This passes through our origin. How do you think the limit's going to behave if y behaves this way and x approaches 0 in value? All right. If we consider its behavior, right, as a limit, right, again, where y is equal to x squared minus x, right, and let's add in there, again, and x approaches 0 in value, the limit we would prepare would be this limit seen here. All right, this limit statement seen here. The limit is x heads to 0, and y is equal to x squared minus x in value. And if I make that y and x squared minus x, my denominator will turn into this statement seen here. It'll be x plus x squared minus x in value. Where certainly you can see that does simplify quite nicely in my denominator. An x minus an x, right? The x term minus the x at the end here, they cancel or add together to give you 0. So you're left with x squared plus 0, or just an x squared in that denominator, and what you end up building is the statement x squared over x squared in value, where it doesn't take much thought there to note that that all simplifies to 1 in value. Where what's the limit as x heads to 0 for the constant of 1? Well, the limit of any constant is the value of the constant. So the result here would be 1 in value. Notice, folks, this 1, what seems a little obscure in its description, right? This one path that seems a little obscure in its description, right, does produce a different value for this limit. All right? Note, not every path that passes through that origin, not every infinite approach gives us the same result here, folks. Here we see a result of 1, whereas we had noted above, all of our linear approaches are going to give us the value of 0. But as I had also highlighted above, right, we had still were not able to conclude that 0 was our result with 100% certainty. As we see down below, there is certainly a path here that gives us a different result. The path where y equals x squared minus x, and x is allowed to approach the value of 0. Right? When we approach the origin in the domain of this function along y values that behave according to this parabola, as x approaches 0, meaning we come down the parabola this way, or we approach from the vertex this way as x approaches 0, right, along that parabolic path. Right? we see a different result for this limit. We see the value of 1. Right? Thus, by the two-path test for non-existence, this limit does not exist. Right? Thus, since this limit yields two different values along two different paths approaching 0, 0 in the domain of this function, right? We cannot conclude from the two-path, or we can conclude, not we cannot, we can conclude. I was reading the not from down below here. We can conclude from the two-path test for non-existence, this limit does not exist, folks. All right? Now, right, we have shown using, right, this one path and our exploration seen above for these different linear paths that we can produce two different paths that do not give the exact same value for the limit. Now, there's probably a big question as to what magic did I use, right, to find that obscure path, right, that produces this different behavior value for the limit, right? Now, how does one know to search deeply for a path of different behavior for this limit, right? And that would have to be a rather deep, intense search to find x squared minus x, or at least appear to be, right? Considering there's an infinite number of different paths to search for, right? Well, an examination of the level curves around this point of interest, right, in the limit should be performed, folks, right? This is where examining your level curves and examining what your graph might look like around this point of approach in your limit is going to be useful, right? If we take note, consider the level curves for the function in this limit, right? I illustrate several level curves down below here. Right? If I was to make several level curves, right, all for a portion of this surface that focuses in on the approach at 0, 0, this is the illustration I get for all several of those level curves. I think this is for like 6 or 7 of those level curves. 6 if we count them out. And in fact, the one that I've highlighted in magenta is the one path that we had noted that was our path of approach seen above. You can see it as one of those respective level curves. And notice how all those level curves appear to behave. What does each and every one of those level curves appear to have in common? And then remember what those level curves show us. Those level curves show us paths in our domain where we have consistent output values for z. This is a path in our domain where we have one set of consistent output values for z. That path, we had note, by examining our limit, must consistently give us the value of 1. We would see that along that path. This is another path that might give us another consistent value for z. That might give us the value of 2. This one might give us the value of z equal to 3. This might be the path at z equal to negative 3. This might be the path at z equal to negative 2. This might be the path at z equal to negative 1. In fact, I think they are. Right? This function can never produce a zero path and output a 0, so the path at 0 is actually undefined. Right? You're not going to have a path where you'll find a level curve appear at 0. It's the way the surface behaves. Right? Due to the format of that being rational. The numerator would have to be 0 when the denominator is not. I think based upon our conditions, that can never happen. Let me be careful with that. But we do note, what do all these level curves have in common? Right? If you take note, what do they all have in common right here? At our approach point, the location of our approach. Well, they all pass through that location, folks. Each and every one of these level curves passes through that location. And what did we say about each and every one of these lines? Each and every one of these lines represents a different output value for our dependent value, for the output of our function, for the z value, right? When our x and y values are on those lines. So if I put myself on this approach, I could potentially have a limit give me the result of 2. And if I put myself on this approach, I might potentially have a value, the limit give me 3. Whereas when I was out here on these other approaches that I don't see as level curves, those are approaches that gave me outputs of 0, respectively. Right? Which should work, right? Yeah, there are level curves out there that produce 0. There's actually a bunch of level curves, right, out there. Every linear approach would have some result that I should be careful with that still. All right. But it puts us out here, right, where you notice we're not on the level curves, right? And you can note how those are behaving. If I actually look at this level curve, that approach that we were able to show non-existence with, right, is the level curve for where z equals 1. Right? For the level curve where z equals 1, we could say f of x comma y equal to x squared over x plus y would be equal to 1 in value. Right? Which implies x squared would be equal to x plus y, or y must be equal to x squared minus x. Notice this description of y. That is the path that I used to prove non-existence up above. All right? That is how I found that mysterious path of non-existence. Right? I knew by examining my level curves that I could produce several different values of z, where at the origin I would have different outputs of the function. Right? Due to the behavior of the surface at this location. Right? Well, as we approach this location. Right? At the location, we know the surface just doesn't exist. But as we approach this location, depending on what path of approach we're on, we're going to actually be approaching different output values for z. I knew I could get an output of 1 on this approach. Right? So I selected that approach in my proof of the non-existence. You're going to want to look at the level curve behavior around your coordinate of approach, folks. If you see your level curves, several level curves passing through that origin, there's a good chance, or passing through that point of approach, there's a good chance, right, that limit does not exist at that value, that you can show using some of the approaches that pass through that origin, right, that you get 2 different values for z, right, which is what the level curves are showing you. They're showing you all the different x, y values that would exist that produce one specific value of z. These are the cases where z is equal to 1 in value. And the origin can be seen there. Here's the case where z equals -1. And the origin can also be seen to behave that way, or the function can be seen to approach -1 in value along that approach. All right? That is where that mysterious, or that approach was found with a deeper, a delve further into our descriptions of approach. All right? Also note the behavior for all level curves where z equals z null. Right? When I let z equals z null be some arbitrary value, and I consider how will all the level curves then behave, right? This will end up implying this. Right? Divide both sides by z null, multiply both sides by x plus y. I can obtain, this statement. We're solving for y. I can subtract x from both sides, and I can make this statement here. Y would be equal to this, or y would equal this statement here, where every single level curve can be shown to actually pass through the origin of the system, right? The origin in our domain. Or our domain produces an infinite number of different level curves on different approaches of our origin here, right? All of them differing by, right, this little z null down in our denominator of the second factor. We were just looking at the case where z null was equal to 1. At z null equal to 2, I could plug in 2 there and I could find a different approach. For a z null of 3, I could plug in a 3 here and find a different approach. Or negative 1, I could plug in negative 1 here and get a different approach that's going to give me a different value for the output of that limit, right? Or for the output of that function, folks. All right. That's another way to start analyzing the level curve behavior at that point of interest. And what you will notice is 0 can be plugged in there and 0 can be plugged in there, and it doesn't matter what the z null is. Those will describe every single, what we might say is level curve, right? That illustrates an approach at the origin in the system. Right? Since x comma y equal to 0, 0 satisfies this equation for every arbitrary value of z equal to z null, we can conclude every level curve in the domain of f will pass through the origin where x comma y is equal to 0, 0. This in turn indicates at this location an infinite number of results for a limit are possible. And thus the value of this limit does not exist for the function at the coordinate 0, 0. All right. I didn't include an illustration of the surface here, folks. We might be able to click over to that. If we were to go over and just look at an illustration of the surface real quick. Myself over here is that surface. All right. Here's its illustration from above along its domain. Now, there are portions of the surface we can't quite see because they go outside of the bounding box for the surface, and that's what's highlighted in gray here. And what we can see is almost everything in our domain is included except for along this line where y would equal negative x. All right. But notice how the surface behaves as we converge upon that line. Depending upon what portion of the domain we're approaching in, right? If I was approaching on a line, yeah, it's certainly passing through the origin. I might pass or be heading towards that value down here kind of at this pinch point. This value that gives me an output of 0. But if I was to approach along that line, let's see if I can grab it here. It's actually the curve. Let's see if I can flip it into proper. All right. Oh, let's go all the way around. Get my x, positive x moving in this direction here. All right. One of the approaches we just looked at was along this parabolic approach. And that was kind of swooping down and through my graph seen right here. And along that approach, I do not actually approach the origin. I'm actually up further along the graph here. Right? Actually pinching in on this location here. We can't quite see it because the graph isn't interpolating into that region there. In terms of how it's making the points, it's really not plotting those points to that degree. Now, can I make it plot more points? Plot points. What if I went with like 180? Do I get a refined sense of the graph? It does refine itself a little bit there, I think. What if we were to bump that up to 300? Does it change any of that illustration some? Not much. You can also set a max recursion. Sometimes that helps. Let's go with This is how many times it goes back and forth over and uses points to plot that region. What happens is we're getting so close to the origin in there, we're seeing it get very close to 0, and it's saying, I don't exist. I'm just down here at this point. Right? And it's a really, really fine degree of difference down there. What if we did a 6? You can see it's plotting a lot of points to kind of come up with the surface and interpolation of that surface. So yeah, it's really having a hard time seeing it. If I was to bump that up to 16. You can see the greater you make those numbers, the longer it takes to run. Actually, I should let it run fully. We are at about an hour and 5 minutes here, folks. The study of limits is tricky. Let me say that as this runs and see if we can give it enough time to run out. Yeah, well, limits are tricky, folks. You do have to explore the level curves. I'm going to come back and show you a Mathematica demo where I'm going to show you how to build your surfaces, certainly in 3 dimensions, how to do some graphing and plotting in these 3-dimensional spaces, folks. Where we might come back and look at this surface and look at plotting a line on this surface here. This function is not going to go away. It does certainly have some interesting behavior, as you take note. Right. This is what it does look like if we start to look at points in its graph. Right. But some of the points are a little tricky to see due to the refinedness. Yeah, we ran out of... It's limited to 15 max recursions. I went 16, 1 over the max limit. But you can see how long that was taking to run there, folks. It was certainly taking a bit of time. Let's see if we can speed it up a little bit. All right. But you can see here I have a lot of code I'd like to share with you. I'm putting these together and looking at limits of functions and doing a bit of an analysis. In fact, I was writing some of that below here. Here is looking at those level curves at that point. And the code to produce that is rather brief. And I'll share this with you, folks, in a demo. Let's go see if that finished up above. It's still running. I don't think we're going to let that run out. Let's just get rid of all that. Go with this. Get back to our surface. We don't have to go up and abort the evaluation. We may. All right, folks. But we'll go back to our notes here. We did see that surface in general. I will point out here, folks, this is evaluating limits. This is the process. Right? Hopefully we have continuity. If we have continuity, folks, what you're going to see in the level curves is you won't see level curves passing through your point of approach. Right? In the case for continuity, right, you definitely won't have level curves passing through, and in case of, I should say, limits that do exist, your level curve behavior is going to be certainly different. You're not going to see all these level curves converging on this one point. Illustrating that at that one location in your domain, you can have all these different potential z values, which I should be careful there. In your approach in that domain, you're approaching all these different z values. You don't actually exist in that location in your domain. That's what's causing the issue in continuity. All right. That is evaluating limits of multivariable functions. The game has changed significantly. Right? And it's changed significantly because we are having to look at an infinite number of approaches. Before it was just 2. It was left and right, and if they equaled the same thing, that it existed and it was that value. Right? If they both went up to positive infinity, it was positive infinity. If they both went to negative infinity, it was negative infinity. But here you can have an infinite number of different approaches in your domain. Right? There are an infinite number of ways you can approach this coordinate. You can see here, this illustrates 6 different approaches that all produce different outputs. And they're all level curves that pass through that origin, folks. It's an analysis of your level curves that is going to help conclude some of these limits in more obscure cases. these indeterminate situations, right? Where you may have to look at several approaches, right? If your approaches don't match up with level curves, or if you can show that no level curve really passes through that point, you're going to be a lot more likely to have what you have seen in your examination of several cases of that limit be the actual value of that limit. But again, you're not 100% certain. It is a bit of a weighted coin flip at that point in time, or a weighted dice flip, you might say. All right, a dice roll. Yeah. Questions over any of this? Questions. Yeah. I'll look for those in class, folks. But this lecture is at 110 minutes. Well, 110. It's at 70 minutes, an hour and 10 minutes. So I am going to end there. But this certainly gets into the intricacies of showing a limit does not exist and how you can analyze the function to see some of that, especially in the more obscure cases. All right. Hope you're doing well, and I'll look for those questions in class. See you then, folks.